Think about the last time you had a truly awful morning. Not just one of those mornings where the coffee takes a little longer to kick in, or where you hit the snooze button one too many times. I mean, one of those mornings where you opened your eyes and it felt like your brain was wrapped in wet concrete, where the light coming through the window seemed almost aggressive, like the world was demanding something from you before you had anything left to give. Your body was awake, technically, but your mind was somewhere else entirely, still buried under layers of fog so thick you could barely remember what day it was, let alone why your alarm was going off. We have all had mornings like that, and most of us, when they happen, reach for the same explanation. I just did not sleep well. Or maybe we blame the late dinner, the extra glass of wine, the argument before bed, the stress from work, the fact that our kid woke us up at 3 in the morning. We treat these terrible mornings as random inconveniences, little glitches in an otherwise manageable routine. We push through them, we pour an extra cup of coffee, we tell ourselves tomorrow will be better. But here is the thing nobody tells you, the thing that changed how I understood my own mornings entirely. Those awful mornings are not random. They are not glitches. They are the direct, measurable, biologically predictable result of what happened while you were unconscious for the previous 6, 7, or 8 hours. And the mechanisms behind them are so specific, so precisely orchestrated by your brain and body, that once you understand them, you will never look at your mornings the same way again. This is not a video about how to become a morning person. It is not about productivity hacks or miracle routines. This is about what is actually happening inside your body from the moment your brain starts to surface from sleep to roughly noon, and why the quality, timing, and structure of last night's sleep is the single most powerful force shaping every aspect of how you feel, think, decide, and perform during those critical first hours of the day. We are going to go deep on this. We are going to talk about a hormone surge that happens before you even open your eyes, one that essentially programs the trajectory of your entire morning. We are going to look at why your brain, in those first minutes after waking, is performing at roughly the same level as someone who is legally intoxicated. We are going to explore why a bad night of sleep does not just make you tired in the morning, it fundamentally rewires how your body processes the breakfast you eat, how your brain makes decisions about food, and why you crave garbage at 10 in the morning after a rough night. We are going to talk about why some people wake up feeling electric at 5:30 in the morning and others cannot form a coherent sentence until noon, and why that difference is not about discipline or willpower, but about something coded deep into your DNA. We are going to look at what morning light does to your brain, why your body temperature at 6 in the morning matters more than you think, and why that cup of coffee you drink the moment your feet hit the floor might be doing something very different from what you believe. And all of it, every single piece, comes back to sleep. Not sleep in some vague, get more rest kind of way, but the specific architecture of what happened in your brain last night. How long you spent in each stage of sleep, when you woke up relative to your internal clock, and whether the biological systems that are supposed to reset and restore overnight actually got the chance to do their job. So settle in. This is going to be a long one, and by the end you are going to understand your mornings better than you ever have before. The cortisol awakening. Response: your morning launch sequence. Let us start with something that happens before your alarm goes off, before your eyes open, before you have any conscious awareness that a new day has begun. Somewhere in the last phase of your sleep, deep inside the architecture of your brain, a biological launch sequence initiates. And it centers on one hormone that most people know only as the stress hormone: cortisol. Now, cortisol gets a terrible reputation. In the wellness world, it is practically a villain associated with belly fat, anxiety, burnout, everything you want to avoid. And yes, chronically elevated cortisol is genuinely harmful. But cortisol in the right amount, at the right time, is one of the most important molecules your body produces. Without it, you literally could not get out of bed. You could not mobilize energy, regulate your blood pressure, or activate the neural circuits that allow you to think clearly. Cortisol in the morning is not your enemy. It is the chemical ignition key that starts your entire day. And the way it activates in the morning is not gradual. It is not a slow trickle. It is an explosion. Researchers call it the cortisol awakening response, or CAR, and it is one of the most dramatic hormonal events your body produces on a daily basis. Within 30 to 45 minutes of waking, your cortisol levels surge by 50 to 75% above your baseline. That is an enormous spike. To put it in perspective, few other events in your daily life produce that kind of hormonal acceleration. It is as if your body, having been in a state of deep metabolic conservation all night, suddenly hits the accelerator and floods your system with the chemical equivalent of biological jet fuel. This surge does not happen randomly. It is orchestrated by a dual control system that involves two of the most sophisticated timing mechanisms in your body. The first is your suprachiasmatic nucleus, the tiny cluster of neurons in your hypothalamus that serves as your master circadian clock. This clock has been tracking time all night, even while you are unconscious, and as dawn approaches, it begins preparing your body for the transition from sleep to wakefulness. The second controller is your hippocampus, the memory center of your brain, which appears to modulate the CAR based on anticipated demands. Your brain, even while sleeping, is essentially forecasting the coming day and calibrating this cortisol surge accordingly. What does the CAR actually do? Think of it as a massive energy mobilization event. That surge of cortisol triggers your liver to release stored glucose into your bloodstream, providing immediate fuel for your brain and muscles. It increases your heart rate slightly, bringing your cardiovascular system up to waking operating levels. It enhances the sensitivity of your immune system, preparing your body for the microbial encounters of the day ahead. And critically, it acts on your brain, increasing arousal, sharpening attention, and beginning the process of clearing the neurochemical fog of sleep. By about 45 minutes after waking, if everything has gone well, you should be experiencing the peak effects of this response. Researchers have found that a healthy CAR is associated with significantly higher levels of subjective arousal and significantly reduced feelings of fatigue at the 45-minute mark, compared to people with a blunted response. In other words, how energized, sharp, and ready you feel at around 7:30 or 8 in the morning, if you woke at 7, is largely a reflection of how robust your cortisol awakening response was. And here is where sleep enters the picture in a way that changes everything. The CAR is not automatic. It is not guaranteed. It depends profoundly on the sleep that preceded it. Research has shown that sleep duration directly modulates the timing and magnitude of this cortisol surge. When people get around 9 hours of sleep, their cortisol levels are already climbing toward their peak before they even wake up. The launch sequence, so to speak, is well underway by the time consciousness arrives. But when sleep is restricted to 6 hours or less, the cortisol peak shifts. Instead of peaking before or right at the moment of waking, it peaks after waking, sometimes significantly later. The launch sequence is delayed. The engine is still cold when you are trying to drive. This is why, after a short night of sleep, the first hour of your morning feels so fundamentally different from a well-rested morning. It is not just that you are tired, it is that the hormonal cascade responsible for activating your entire system is running behind schedule. Your brain is awake, but the chemical support system that makes wakefulness feel productive and purposeful is still catching up. And it gets more nuanced than just duration. The consistency of your wake time also matters enormously. If you wake at 6:30 on weekdays and 9 on weekends, you are introducing what researchers call social jet lag. And this disruption throws off the timing of your car in ways that can persist for days. Irregular wake times essentially confuse the dual control system. Your suprachiasmatic nucleus is trying to predict when you will wake based on your recent history, and if that history is inconsistent, the prediction fails. The cortisol surge comes too early or too late, or at a reduced magnitude. The result is that Monday and Tuesday mornings feel disproportionately terrible, not because of anything inherently awful about the start of the work week, but because your hormonal launch sequence has been disrupted by the timing inconsistency of the weekend. Chronotype matters here too, and we will get into that in much more detail later. But for now, know this. Morning chronotypes, the people who naturally wake early and feel alert quickly, produce a larger cortisol awakening response than evening chronotypes. And the timing of their cortisol peak occurs roughly 55 minutes earlier than it does for night owls. That is nearly an hour of hormonal head start. When an early riser feels bright and functional at 6:30 in the morning, it is not because they are more disciplined or because they have better habits. It is because their cortisol awakening response fired earlier and harder, setting their entire biochemistry up for a faster morning activation. There is also an important clinical dimension here that is worth mentioning. A blunted cortisol awakening response, one that fails to produce that 50 to 75% surge, is associated with a range of health problems. It is more common in people with type 2 diabetes, insulin resistance, chronic fatigue, and depression. And guess what one of the strongest predictors of a blunted CAR is? Chronic poor sleep. Not just one bad night, but an ongoing pattern of insufficient or disrupted sleep that gradually degrades the responsiveness of this critical morning activation system. So the first lesson of morning energy is this: the single most important event shaping how you feel when your day begins is an invisible hormonal explosion that depends almost entirely on the quality and timing of your sleep. Get it right, and your body launches into the day with precision and power. Get it wrong, and you're trying to start a car with a half-dead battery, wondering why everything feels so sluggish and off. Sleep inertia. Why your brain is drunk when you wake up. Now, let us talk about those first minutes after your eyes open, because even if your cortisol awakening response is perfectly timed, there is another biological phenomenon at work that can make the transition from sleep to wakefulness feel absolutely brutal. And understanding it will change how you think about those groggy, disoriented moments at the start of your day. It is called sleep inertia, and it is one of the most underappreciated aspects of human biology. Sleep inertia is the transitional state between sleep and full wakefulness. And during this period, your cognitive abilities are genuinely, measurably impaired. We are not talking about a subtle difference here. Research has demonstrated that in the first few minutes after waking, your performance on cognitive tasks can be worse than it is after 24 hours of total sleep deprivation. Think about that. In those early moments of your morning, your brain is functioning at a level comparable to someone who has not slept at all. Some studies have found that the impairment is equivalent to having a blood alcohol concentration at or above the legal limit for driving. You are, for a brief window, cognitively drunk. Why does this happen? The answer lies in what is going on inside your skull during those first minutes of consciousness. When you are asleep, particularly during the deeper stages of sleep, your brain operates in a fundamentally different mode than when you are awake. Blood flow patterns are different. Neural firing patterns are different. The electrical signatures of your brain, the brainwaves that researchers measure with EEG, are dominated by slow, rolling delta waves during deep sleep that are completely unlike the fast, irregular patterns of waking consciousness. When your alarm goes off, or when you wake naturally, the transition between these two states is not instantaneous. It takes time. Specifically, it takes time for blood flow to return to full waking levels in the anterior cortical regions of your brain. These are the frontal areas, the prefrontal cortex in particular, that handle your highest level cognitive functions, your ability to make decisions, plan your day, regulate your emotions, focus your attention. Research has shown that it takes 15 to 30 minutes for cerebral blood flow in these regions to reach the levels associated with normal daytime functioning. During that gap, those brain regions are essentially operating on reduced power. The lights are on, but the processors are still booting up. And it is not just blood flow during sleep inertia, delta wave activity. The signature of deep sleep can persist into wakefulness. Your brain has not yet fully shifted its electrical activity from sleep mode to wake mode. There is a neural overlap, a bleed-through of sleep into your waking state that keeps your cognitive machinery running at reduced capacity. The specific cognitive functions most affected by sleep inertia are revealing. Research has identified selective attention as the function that takes the largest hit. This is your ability to focus on what matters while filtering out irrelevant information. Sustained attention, the ability to remain vigilant over time, is also impaired. So is cognitive inhibition, the capacity to suppress impulsive responses and make deliberate choices. Decision-making suffers. Reaction time slows, spatial memory weakens. Basically, every cognitive ability you need to navigate the first moments of your day, from deciding what to eat for breakfast, to remembering your schedule, to not snapping at your partner when they ask you a simple question, is operating below its normal capacity. In most people, under normal circumstances, sleep inertia resolves within 15 to 30 minutes. Your blood flow normalizes, the delta waves dissipate, and your prefrontal cortex comes fully online. But here is the critical part, the part where sleep quality becomes the deciding factor. Sleep inertia is dramatically worse when sleep has been compromised. If you are sleep deprived, sleep inertia does not last 15 to 30 minutes. It can extend to 2, 3, even 4 hours. The impairment is deeper and the recovery is slower. And the reason is straightforward. When you are sleep deprived, your body compensates by increasing the amount of deep, slow-wave sleep it gets. This is a survival mechanism, a way of prioritizing the most restorative stage of sleep when total sleep time is limited. The problem is that waking from deep, slow-wave sleep produces the most severe sleep, inertia. The deeper the sleep you are yanked from, the more dramatic the cognitive impairment upon waking. So if you went to bed late and your alarm drags you out of a deep sleep cycle at 6 in the morning, you are not just dealing with tiredness. You are dealing with a physiological state where your prefrontal cortex is running on fumes. Your blood flow has not caught up, and delta waves are still echoing through your neural circuits. The morning feels impossible not because you lack willpower or motivation, but because the biological machinery that supports willpower and motivation is still offline. This also explains why waking at the same time every day, even on weekends, makes such a profound difference in morning alertness. When your wake time is consistent, your brain learns to time its sleep cycles so that you naturally surface from lighter sleep stages right around your alarm. You emerge from stage 1 or stage 2 sleep, where the transition to wakefulness is gentle and the cognitive impairment is minimal. But when your wake time is inconsistent, your brain cannot predict the timing, and you are much more likely to be pulled out of deep sleep, producing a more severe and prolonged bout of sleep inertia. There are countermeasures, and they are worth knowing about. Research has shown that 100 milligrams of caffeine, roughly the amount in a standard cup of coffee, can reduce the duration of sleep inertia. Bright light exposure in the first few minutes after waking has been shown to accelerate the transition to full wakefulness, in part by potentiating the cortisol awakening response we talked about earlier. And strategic nap timing for those who nap matters enormously, because naps that extend into deep sleep produce their own bout of sleep inertia upon waking. But the single most effective countermeasure to sleep inertia is also the simplest. Sleep enough at consistent times so that your brain can organize its sleep architecture properly and time your awakening to coincide with lighter sleep stages. That is it. That is the foundation upon which everything else is built. Get the sleep right, and sleep inertia is a brief, manageable blip. Get it wrong, and you are spending the first hours of your day in a cognitive fog that no amount of coffee or cold showers can fully dispel. Adenosine, the invisible force behind morning fog. To understand why some mornings feel clear and others feel like wading through mud, you need to understand a molecule called adenosine, and specifically what happens to it, or fails to happen to it, while you sleep. Adenosine is one of the most fascinating substances in neuroscience, and its role in sleep and wakefulness is both elegant and profound. Throughout your waking hours, as your neurons fire and your brain consumes energy, adenosine accumulates as a byproduct of that energy expenditure. Think of it as metabolic exhaust. The longer you are awake, the more adenosine builds up in your brain, particularly in a region called the basal forebrain. After 12 to 16 hours of wakefulness, adenosine levels have roughly doubled from their baseline, creating an enormous biological pressure to sleep. It does this by binding to specific receptors, mainly the A1 and A2A adenosine receptors, on neurons that promote wakefulness. When adenosine binds to these receptors, it inhibits those neurons, essentially putting the brakes on the wake-promoting systems in your brain. The cholinergic neurons of the basal forebrain, which are critical for maintaining alertness and attention, are particularly sensitive to this adenosine-driven inhibition. As adenosine levels rise throughout the day, these neurons fire less and less, and you feel progressively sleepier. This is what sleep scientists call sleep pressure, or homeostatic sleep drive, and it is one of the two primary forces, alongside your circadian rhythm, that determines when you feel sleepy and when you feel awake. Here is the crucial part for our discussion of morning energy. Adenosine is cleared during sleep, not upon waking, not during the first hour of your morning, during sleep itself, and specifically during the deeper stages of slow wave sleep. When you enter deep sleep, a remarkable process occurs. Your brain activates a waste clearance system, sometimes referred to as the glymphatic system, that flushes out metabolic waste products, including adenosine. Over the course of a full night of sleep, With adequate time in deep sleep stages, adenosine levels drop back towards their baseline. By the time you wake up naturally after a complete, well-structured night of sleep, adenosine levels should be low. The sleep pressure should be essentially reset. And that low adenosine state is part of what makes a well-rested morning feel so clean and clear. That sense of waking up refreshed, with a mind that feels sharp and ready rather than heavy and reluctant. But what happens when sleep is insufficient? What happens when you only get 5 or 6 hours instead of the 7 to 9 your brain needs? The answer is straightforward and consequential. Adenosine does not fully clear. You wake up with elevated adenosine levels, residual sleep pressure that your brain did not have enough time to flush out. And those elevated adenosine levels are still binding to those A1 and A2A receptors, still inhibiting the wake-promoting neurons that you need for morning alertness, still dragging on the very neural circuits responsible for attention, focus, and clarity. This is not a subtle effect. Brain imaging studies have shown that after extended sleep deprivation, roughly 52 hours of wakefulness, the availability of A1 adenosine receptors increases by 11 to 14%. The brain is literally creating more parking spaces for adenosine, essentially making itself more sensitive to this sleepiness signal. And while this receptor upregulation is partially restored after about 14 hours of recovery sleep, it does not fully resolve overnight in people who are chronically sleep-deprived. The system accumulates a kind of adenosine debt over time. Interestingly, there appears to be significant individual variation in how sensitive people are to adenosine accumulation. Research has found that individuals who show a larger increase in A1 receptor availability during sleep deprivation are actually more resilient to the cognitive effects of sleep loss. Their brains seem to have a more efficient buffering system. This may partly explain why some people seem to handle a few bad nights of sleep relatively well, while others crumble. It is not just about mindset or toughness. It is about the molecular architecture of your adenosine system, which is largely genetically determined. Now, this is where caffeine enters the picture. And I want to be precise here because there is an enormous amount of misinformation circulating about caffeine, adenosine, and morning timing. Caffeine works by blocking adenosine receptors. It fits into those A1 and A2A receptor binding sites, preventing adenosine from attaching and exerting its inhibitory effects. When caffeine blocks these receptors, the wake-promoting neurons that adenosine would normally be suppressing are free to fire at full capacity. That is why caffeine makes you feel alert. It is not creating energy, it is removing the chemical brake on your alertness system. But here is what caffeine does not do. It does not clear adenosine from your brain. The adenosine is still there. Caffeine merely masks its effects by blocking the receptors. This is an important distinction, because when the caffeine wears off, that adenosine is waiting, ready to bind, and the crash you feel is the delayed expression of all the sleep pressure that was building up while the receptors were blocked. This means that if you wake up after a bad night of sleep with high residual adenosine levels and immediately drink coffee, you are not solving the problem. You are masking it. The adenosine is still elevated. The underlying sleep debt is still present. The coffee is simply blocking your ability to feel it. And when it wears off, usually 4 to 6 hours later, the accumulated adenosine hits those receptors all at once, and you crash harder than you would have if you had just dealt with the lower energy level from the start. The only thing that actually reduces adenosine levels is sleep, specifically deep, slow-wave sleep. There is no supplement, no biohack, no breathing technique that replicates what deep sleep does for adenosine clearance. When people say they feel restored after a good night of sleep, a significant part of what they are describing is the experience of waking up with low adenosine, a neurochemical slate that has been wiped clean, a brain that is ready to accumulate fresh sleep pressure throughout the new day, rather than starting with yesterday's leftovers. This is why cumulative sleep, debt, is so insidious. Each night of insufficient sleep leaves a little more adenosine uncleared. Each morning starts with a slightly higher baseline of sleep pressure. Over days and weeks, this accumulates into a chronic state of elevated adenosine that feels like a permanent fog, a baseline of fatigue that people often mistake for aging, or depression, or just the unavoidable cost of a busy life. It is not. It is a sleep debt, and the most powerful tool for repaying it is consistent, adequate, well-timed sleep that gives your brain enough deep sleep to do its janitorial work properly. Your morning blood sugar. How last night's sleep rewires your metabolism. Let us shift now from what is happening in your brain to what is happening in the rest of your body. Because the effects of sleep on morning energy extend far beyond neurotransmitters and hormones. They reach directly into your metabolism, specifically into how your body handles glucose, and the implications for how you feel. Before noon are enormous. Glucose is your body's primary fuel source. Your brain, despite making up only about 2% of your body weight, consumes roughly 20% of your total glucose supply. Your muscles rely on glucose for movement. Your organs need it for their basic operations. How efficiently your body manages this fuel, how well it shuttles glucose from your bloodstream into the cells that need it, is one of the most fundamental determinants of how energetic or sluggish you feel at any given moment. And sleep, it turns out, is one of the most powerful regulators of glucose metabolism. Not in some vague, general sense, but in a specific, measurable, clinically significant way that manifests most dramatically in the morning hours. Here is what happens after just one night of inadequate sleep. Not weeks of chronic sleep deprivation, not months of pulling all-nighters. One single night. Research has shown that a single night of sleep deprivation reduces insulin sensitivity by 16 to 24%. That is a staggering change from just one bad night. Insulin is the hormone responsible for moving glucose out of your bloodstream and into your cells. When your cells become less sensitive to insulin, glucose stays elevated in your blood. Your pancreas has to work harder, producing more insulin to achieve the same effect. And despite those elevated insulin levels, the glucose clearance is still impaired. What does this feel like? It feels like a morning where your energy is flat, where your brain feels foggy, where you cannot quite think clearly despite having technically eaten enough. Your brain is sitting in a bath of glucose that it cannot efficiently access. The fuel is there, circulating through your bloodstream, but the doors into your neurons are partially closed. It is like having a full gas tank with a clogged fuel line. The specific pattern of this metabolic disruption is revealing. After sleep deprivation, morning glucose levels tend to be higher than normal, and they remain elevated through mid-morning into the late afternoon. This is not because you ate differently or consumed more sugar. It is because your body's ability to process glucose was fundamentally impaired by the sleep loss. Your cells are resistant. Your insulin is working overtime but achieving less. And the downstream effect is a morning that feels heavy, brain-fogged, and low on usable energy, despite there being plenty of fuel in your system. And if one night is bad, the cumulative effects are significantly worse. Studies where researchers restricted subjects to 4 to 5 hours of sleep per night for several consecutive nights found a 40% reduction in glucose tolerance. 40%. The acute insulin response, the body's immediate reaction to a glucose load, was significantly diminished. In healthy young adults with no prior metabolic issues, just a few days of sleep restriction produced a metabolic profile that resembled the early stages of type 2 diabetes. This has profound implications for what happens when you eat breakfast after a poor night of sleep. That bowl of oatmeal, that piece of toast, that banana, whatever carbohydrate-containing food you eat in the morning, your body is processing it differently than it would after a full night of sleep. The glucose spike is higher, the insulin response is less effective, and the energy crash that follows is deeper and more prolonged because your cells are not efficiently absorbing the fuel. There is also a circadian dimension to this that is worth understanding. Your body's ability to process glucose is not constant throughout the day. It is best in the morning and declines as the day progresses. This is one of the reasons why nutritional science has increasingly recognized that when you eat matters, not just what you eat. Your glucose tolerance is naturally highest after a well-rested morning, which means that for most people, breakfast is the meal their body is best equipped to handle metabolically. But here is the cruel irony. When sleep is disrupted, this morning metabolic advantage is eroded. The circadian enhancement of glucose processing is reduced. Research on circadian misalignment, which occurs when your sleep-wake schedule is out of sync with your internal clock, has shown that the resulting glucose intolerance is primarily driven by reduced insulin sensitivity rather than impaired beta cell function. In other words, your pancreas is still producing insulin normally, but your cells are not responding to it. The signal is there. The receiver is muffled. There is hopeful news here, though. Research has demonstrated that extending sleep can rapidly improve these metabolic parameters. One study found that when people who were habitually sleeping around 6 hours extended their sleep to roughly 10 hours for just 3 nights, their HOMA-IR, a standard measure of insulin resistance, decreased by approximately 20%. 3 nights, a 20% improvement in insulin sensitivity. That is the kind of rapid metabolic improvement that would be remarkable if it came from a drug. And it comes from sleep. The practical takeaway is that your morning energy is not just about whether you feel tired. It is about whether your body can actually access and use the fuel you give it. After a bad night of sleep, you are metabolically compromised. The glucose from your breakfast is being handled inefficiently, leading to higher blood sugar, less cellular energy, more brain fog, and a stronger likelihood of an energy crash before lunch. After a good night of sleep, that same breakfast is processed smoothly. Glucose enters your cells efficiently. Your brain gets the fuel it needs, and your energy through the morning is stable and sustained. Sleep does not just affect how you feel. It affects how your cells function at the most basic level of energy production. And nowhere is that more consequential than in the morning hours when you are trying to fuel up for the day ahead. The morning brain. Why poor sleep makes you stupid before noon. We have talked about hormones and metabolism. Now let us talk about what might be the most alarming consequence of poor sleep on your morning. The direct, measurable degradation of your cognitive abilities and, specifically, what happens to the most advanced part of your brain when it does not get the rest it needs. The prefrontal cortex is the crown jewel of human cognition. It sits right behind your forehead, and it is responsible for essentially everything that makes you functionally human in a modern context. Executive function, the ability to plan, organize, and sequence complex tasks. working memory, the capacity to hold and manipulate information in your mind. Emotional regulation, the ability to manage your reactions rather than being controlled by impulses. Decision-making, especially decisions that require weighing, competing options and considering long-term consequences. Cognitive flexibility, the ability to switch between different tasks or mental frameworks. All of these are prefrontal cortex functions, and all of them are disproportionately vulnerable to sleep loss. Brain imaging studies have painted a vivid and concerning picture of what happens to the prefrontal cortex after poor sleep. After 24 hours of sleep deprivation, functional MRI studies show significantly reduced activation in the dorsolateral prefrontal cortex during working memory tasks. Metabolic activity, measured through PET scans, drops in both the prefrontal cortex and the thalamus, the relay station that funnels sensory information to the cortex for processing. The prefrontal cortex is not just performing worse, it is literally consuming less energy, operating at a reduced metabolic rate, as if it has been partially powered down. And this is not just a laboratory finding. It manifests in real, measurable ways that show up in your morning behavior. After a poor night of sleep, your selective attention, the ability to focus on what matters while ignoring distractions, takes the largest hit. This is why, on a bad morning, you find yourself reading the same email 3 times without absorbing it, or getting distracted by your phone when you meant to be getting ready for work. Your sustained attention, the ability to remain focused over time, is also degraded. Cognitive inhibition, your capacity to suppress inappropriate or impulsive responses, is weakened. This is why you are more likely to snap at your kids, make an impatient comment to your partner, or say something at a meeting that you immediately regret. Your reaction time slows. Your spatial memory, the ability to navigate your environment and keep track of where things are, deteriorates. Your ability to solve novel problems, to think creatively, to adapt to unexpected situations, all of these take a hit that is most pronounced in the morning hours when your brain is still transitioning from sleep. But perhaps the most consequential effect, the one that colors your entire morning experience, involves the connection between your prefrontal cortex and your amygdala, the brain's emotional alarm system. In a well-rested brain, the prefrontal cortex maintains a kind of supervisory control over the amygdala. When something annoying or frustrating happens, your prefrontal cortex steps in, moderates the emotional response, provides perspective, keeps you from overreacting. It is the calm, rational adult in the room. After poor sleep, this connection weakens. Brain imaging studies have shown reduced functional connectivity between the prefrontal cortex and the amygdala in sleep-deprived individuals. The rational supervisor is off-duty, and the emotional alarm system is running without oversight. This is why bad mornings do not just feel cognitively dull, they feel emotionally volatile. Small frustrations feel enormous. Minor setbacks feel catastrophic. The traffic, the spilled coffee, the child who cannot find their shoes. All of these take on an emotional weight that is completely disproportionate to their actual significance. You're not being weak or oversensitive. Your emotional regulation circuitry is neurologically compromised by insufficient sleep. This effect is particularly pronounced in the morning because of the compounding influence of sleep inertia. Remember, the prefrontal cortex is the last region to fully come online after waking. It takes 15 to 30 minutes for blood flow to reach normal levels in these anterior cortical areas. If you are also sleep deprived, that recovery is slower, and the baseline you are recovering to is already impaired. You are dealing with a double deficit. the normal transitional impairment of sleep inertia layered on top of the broader cognitive degradation caused by insufficient sleep. The result is a morning where your brain is functionally operating at a fraction of its capacity. Your ability to plan your day is reduced. Your working memory is diminished. Your emotional responses are amplified and poorly regulated. Your attention wanders. Your decisions are more impulsive and less considered. And all of this happens in the first few hours of the day, the hours that often set the tone for everything that follows. This is why so many people describe the experience of a bad morning as feeling like they are operating behind a pane of glass, or underwater, or through a thick fog. These are not just metaphors. They are surprisingly accurate descriptions of a brain that is genuinely, measurably impaired, a prefrontal cortex that has been denied the restoration it needs, and is now struggling to perform the functions that modern life demands of it. And the recovery, when it comes, is not linear. It is not as if you feel terrible at 7 and fine by 9. The cognitive impairment from sleep deprivation can persist throughout, the entire morning and into the afternoon. Some studies have found that certain cognitive functions remain impaired even after what seems like a full night of recovery sleep. The brain prioritizes restoring the most critical functions first, and some of the more subtle aspects of prefrontal function can take days of adequate sleep to fully recover. The message here is not meant to be alarming, though it probably is. It is meant to be clarifying. When you have a morning where you feel dull, unfocused, emotionally reactive, and unable to think clearly, you are not imagining it. Your brain is genuinely impaired, and the cause, in the vast majority of cases, is not some mysterious neurological issue. It is that you did not get enough high-quality sleep, and the most advanced, most metabolically demanding, most sleep-dependent part of your brain is paying the price. The hungry morning. How sleep deprivation hijacks your appetite. Now let us talk about one of the most insidious ways that poor sleep sabotages your morning, one that most people experience without having any idea what is driving it. I'm talking about the way sleep deprivation fundamentally alters your appetite, your food preferences, and your ability to make good decisions about what you eat, all starting from the moment you wake up. If you have ever noticed that after a bad night of sleep, you wake up ravenously hungry with a specific craving for sugary, starchy, high-calorie food, you are not imagining it. And you are not lacking discipline. You are experiencing a coordinated biological assault on your appetite regulation system that is driven by at least 4 separate mechanisms, all triggered by insufficient sleep. The first mechanism involves ghrelin, the hunger hormone. Ghrelin is produced primarily in the stomach, and its job is to signal to your brain that you need to eat. It rises before meals and falls after eating. After sleep deprivation, morning ghrelin levels increase by roughly 22%. That is a significant spike in a hormone whose entire purpose is to make you feel hungry. You wake up with a belly that is screaming for food, not because you burned extra calories during the night, but because your hormonal signaling has been altered by the sleep loss. The second mechanism involves leptin, the satiety hormone. Leptin is produced by your fat cells and signals to your brain that you have adequate energy stores. When leptin levels are high, you feel satisfied. When they are low, you feel hungry. Sleep deprivation either decreases leptin levels or, in some study designs, leaves them unchanged but reduces the brain's sensitivity to the signal. Either way, the result is the same. Your brain receives a weakened message that you are satisfied, making it harder to feel full and easier to keep eating. But the third mechanism might be the most fascinating and the least well-known. It involves the endocannabinoid system. Yes, the same system that is activated by cannabis. Your body produces its own cannabinoid-like molecules, and one of the most important is called 2-AG, or 2-arachidonylglycerol. Research has found that after sleep deprivation, circulating levels of 2-AG increase by roughly 33% above normal, and the timing of this increase is particularly revealing. Normally, 2-AG peaks in the early afternoon. After sleep deprivation, the peak is delayed by about 90 minutes, and the elevated levels persist well into the evening, remaining high until around 9 at night. What does elevated 2-AG do? Exactly what you would expect from a cannabinoid signal. It increases the hedonic drive for food, the pleasure and reward you experience from eating, particularly from foods that are high in fat, sugar, and calories. It is the biological equivalent of having the munchies, driven not by cannabis, but by sleep loss. And it begins affecting your morning food choices from the moment you start thinking about breakfast. The fourth mechanism ties back to the prefrontal cortex impairment we discussed earlier. Brain imaging studies have shown that after sleep deprivation, the prefrontal cortex shows diminished activity during food-related decision-making tasks, while the amygdala shows increased reactivity to images of high-calorie food. The rational, controlled part of your brain that would normally say, "No, I do not need a donut for breakfast," is weakened. The emotional, reward-driven part of your brain that responds to the sight and smell of high-calorie food is amplified. The result is a tilt in the balance of your food decision-making system, away from deliberate, health-conscious choices and toward impulsive, reward-seeking consumption. Add all four of these mechanisms together, and you have a perfect storm of appetite dysregulation. You wake up hungrier than normal because ghrelin is elevated. You feel less satisfied from eating because leptin signaling is blunted. The pleasure you get from eating high-calorie food is amplified because your endocannabinoid system is in overdrive. And your ability to exercise self-control around food is compromised because your prefrontal cortex is impaired. This is why, after a bad night of sleep, you reach for the pastry instead of the eggs. You add extra sugar to your coffee. You grab a muffin on the way to work. You eat more at breakfast than you intended, and still feel hungry an hour later. None of this represents a failure of willpower. It represents the coordinated effects of multiple biological systems that have been destabilized by insufficient sleep, all converging on the same outcome: overconsumption of calorie-dense food in the morning. And the metabolic consequences compound the problem. Remember what we discussed about glucose regulation. After poor sleep, your insulin sensitivity is reduced. So the high-sugar, high-carbohydrate breakfast that your sleep-deprived brain is craving is precisely the type of meal that your sleep-deprived metabolism handles worst. The glucose spike is higher, the insulin response is less effective, and the resulting crash is deeper and comes sooner. By mid-morning, you are in an energy trough that sends you reaching for another snack, another coffee, another dose of quick sugar, perpetuating a cycle of metabolic instability that would not have started if you had simply slept well. There is also emerging research on how sleep deprivation affects the gut hormones that regulate satiety after meals. GLP-1, glucagon-like peptide 1, is one of the key hormones released by your intestines after eating that signals fullness to your brain. Research suggests that sleep loss impairs the GLP-1 response to meals, meaning that even after eating a full breakfast, the signal that says you have had enough is weakened. This contributes to the phenomenon of eating a substantial morning meal and still feeling unsatisfied, still looking for something more, unable to generate the sense of completeness that normally follows a meal. The morning after poor sleep, then, is not just a morning of tiredness. It is a morning of metabolic compromise compounded by appetite hijacking. Your body cannot handle fuel efficiently, and simultaneously, your brain is driving you to consume the worst possible fuel in the largest possible quantities. It is a metabolic double bind, and the only way out of it is to address the root cause. Not with more willpower, not with a stricter diet, not with a meal prep system, but with better sleep. Why your neighbor bounces out of bed at 5 and you cannot function until noon. The science of chronotypes. Let us now address something that has probably bothered you for years, something that has been a source of guilt, frustration, or confusion for millions of people. Why is it that some people wake up naturally at 5:30 in the morning, fully alert, practically vibrating with energy, ready to run or read or cook an elaborate breakfast, while others could not form a coherent thought at that hour if their life depended on it? The standard explanation is that early risers are more disciplined, more motivated, more committed to their health. The late risers are lazy, undisciplined, making poor choices. This narrative is everywhere. It is in productivity books, motivational podcasts, corporate culture. The 5 a.m. club, the miracle morning, the early bird gets the worm. This narrative is wrong, not just incomplete, fundamentally wrong, and the science proving it is wrong has been accumulating for decades, reaching a point where continuing to perpetuate the myth of universal morning superiority is not just misguided, it is genuinely harmful to the roughly 30% of the population who are genetically wired for a later schedule. Your chronotype, your natural tendency toward earlier or later sleep and wake times, is one of the most strongly genetically determined behavioral traits we know of. Research estimates that 40 to 48% of the variation in chronotype between individuals is heritable. That is an enormous genetic contribution. More than 350 gene variants have been identified that influence whether you are a morning person or an evening person, including well-characterized genes like PER3, a core component of the molecular clock that runs in every cell of your body, and RGS16, which helps regulate the pace of that clock. Sleep researchers generally categorize people into 3 broad chronotypes, though it is really a continuous spectrum. About 15% of the population are early chronotypes, sometimes called lions, who naturally wake early, peak in energy and cognitive function in the morning hours, and begin declining in the afternoon and evening. About 55% are intermediate chronotypes, sometimes called bears, whose schedule roughly follows the solar cycle. And about 30% are late chronotypes, sometimes called wolves, who naturally gravitate toward later sleep times, reach their peak cognitive and physical performance later in the day, and function poorly in the early morning. Now, here is what matters for our discussion of morning energy. These chronotype differences are not just about preference. They are reflected in measurable biological differences that directly affect how you feel before noon. Morning chronotypes produce a larger cortisol awakening response than evening chronotypes. Their cortisol peak occurs roughly 55 minutes earlier. That is nearly an hour of biochemical head start. While the night owl is still struggling through severe sleep inertia at 7 in the morning lark's cortisol surge has already peaked and is actively fueling their cognitive function, emotional regulation, and physical energy. But the real problem for evening chronotypes is not just their natural biology. It is the collision between their biology and the demands of modern society. We live in a world that is structured around an early schedule. Work starts at 8 or 9. School starts at 7 or 8. Social expectations assume that productive hours are morning hours. And for evening chronotypes, meeting these demands requires chronic circadian misalignment. Waking hours before their biological clock has prepared them for wakefulness, sleeping at times when their body is not yet ready for sleep. This chronic misalignment has a name: social jet lag, and it affects a staggering proportion of the population. Studies estimate that 67 to 80% of people experience at least some degree of social jet lag, a mismatch between their biological sleep timing and their socially imposed sleep timing. The average mismatch is about 1 to 2 hours. But for extreme evening chronotypes forced onto early schedules, it can be 3, 4, or more hours. Social jet lag is not just about feeling groggy on Monday morning. It has measurable health consequences that accumulate over time. Research has found that each hour of social jet lag is associated with a 20% increase in cardiovascular risk, increased rates of obesity and metabolic syndrome, and higher rates of depression and behavioral problems. Evening chronotypes who are chronically forced onto early schedules show a 2.5 times higher likelihood of reporting poor overall health compared to morning chronotypes. They have a 2.5 times increased risk of type 2 diabetes, a 20% higher risk of obesity, a 30% higher risk of metabolic syndrome, and a 30% higher risk of hypertension. These are not subtle differences. These are massive risk elevations that arise largely because a significant proportion of the population is chronically sleeping against their biological clock. And all of this manifests most acutely in the morning. When an evening chronotype forces themselves awake at 6:30 for work, they are not just waking up early. They are waking up during what their body considers the middle of the biological night. Their cortisol awakening response is weak because their circadian system was not ready for it. Their body temperature is still near its overnight low because it had not yet begun its natural pre-waking rise. Their melatonin may still be circulating because their clock has not yet signaled for its suppression. They are, in every biological sense, functioning in the wrong time zone. The morning feels terrible for these individuals, not because they are doing something wrong, not because they are not committed enough to good habits, but because their genetics have placed their biological clock on a different schedule than the one society imposes. And the cumulative toll of fighting this mismatch, day after day, month after month, year after year, shows up in both their morning experience and their long-term health. The solution is not to force everyone into an early schedule and hope they adapt. The science is clear that chronotype is largely fixed and resistant to behavioral modification. Evening chronotypes cannot train themselves to become morning people any more than a morning person can train themselves to be productive at midnight. The solution involves recognizing chronotype as a genuine biological trait, building flexibility into work and school schedules where possible, and understanding that when someone says they are not a morning person, they are making a statement about their genetics, not about their character. For those who must wake early despite a late chronotype, the most important mitigation strategies involve maximizing sleep quality within the constraints they face, using morning light exposure to partially advance their circadian rhythm, and being realistic about what their biology can and cannot do in the first few hours after an early alarm. And critically, not adding guilt and self-blame to an already challenging situation, because the emotional toll of chronic social jet lag is bad enough, without the additional weight of believing that it is your fault. The morning light switch: how photons program your energy. There is something you can do in the first minutes of your morning that has a more profound effect on your energy, alertness, and circadian alignment than almost any other single action. And it costs nothing, requires no equipment, and takes less than 30 minutes. You can step outside and let morning light hit your eyes. This sounds deceptively simple, almost disappointingly so in a world that wants complicated biohacks and expensive solutions. But the science behind morning light exposure is extraordinarily robust, and the mechanisms through which it operates are some of the most elegant in all of human biology. When morning light enters your eyes, it does not just allow you to see. It hits a specialized population of cells in your retina called intrinsically photosensitive retinal ganglion cells, or iPRGCs. These cells are not involved in forming visual images. They have a completely different job. They detect the overall brightness and spectral composition of the light around you, and they send that information directly to your suprachiasmatic nucleus, the master circadian clock in your hypothalamus. This light signal is the most powerful Zeitgeber, or time giver, that your circadian system receives. It tells your master clock what time it is in the external world, and the SCN uses that information to synchronize all the biological rhythms that govern your physiology, from hormone release to body temperature, to metabolic function, to immune activity. When you get bright light exposure within the first hour of waking, several things happen in rapid succession. First, the light signal to your SCN accelerates the suppression of melatonin, the hormone that promotes sleepiness. Even if your melatonin is already declining naturally as part of the waking process, morning light speeds up that decline, helping to clear the neurochemical signal for sleep more quickly and promoting a faster transition to full alertness. Second, morning light exposure potentiates the cortisol awakening response. The light signal enhances the magnitude of that critical cortisol surge we discussed earlier, making the hormonal launch sequence more robust and effective. This is one of the reasons why waking on a bright summer morning feels so different from waking in the deep darkness of winter, even if you got the same amount of sleep. The light amplifies the biochemical activation that drives morning energy. Third, and perhaps most importantly for long-term circadian health, morning light advances your circadian phase. This means it shifts your internal clock slightly earlier, so that the next night your body begins producing melatonin a little sooner. Your temperature rhythm dips a little earlier, and the entire cascade of biological events that leads to sleepiness occurs at an earlier time. Over days and weeks, this phase advancement helps align your internal clock with your desired sleep schedule, making it easier to fall asleep at night and easier to wake feeling rested in the morning. Research has quantified this effect with impressive precision. Studies have found that morning exposure to blue-enriched light at around 225 lux can produce a circadian phase advance of approximately 84 minutes, plus or minus 51 minutes. Even amber light produces some advancement, around 48 minutes, but blue-enriched morning light, the kind found in natural sunlight, is significantly more effective. What does this mean practically? It means that stepping outside for even 30 minutes in the morning, exposing your eyes to natural light that is typically 5,000 lux or more on a clear day, is providing your circadian system with its most important daily calibration signal. Indoor lighting, by comparison, typically provides only 100 to 500 lux, a fraction of the signal strength that your SCN needs for optimal synchronization. This explains why so many people who spend their mornings entirely indoors, going from bedroom to bathroom to kitchen, to car to office, under artificial lighting, experience chronic circadian drift. Their internal clocks gradually become desynchronized from the external day-night cycle because they are not receiving a strong enough morning light signal to maintain alignment. The result is difficulty falling asleep at the desired time, difficulty waking feeling refreshed, and a general sense of circadian malaise that manifests as low morning energy, afternoon sleepiness, and poor sleep quality at night. There is also fascinating recent research suggesting that caffeine may function as a weak Zeitgeber itself, an external timing signal that can modestly influence circadian rhythms. This effect appears to be strongest when caffeine is consumed closer to the circadian nadir, which for most people occurs in the early morning hours. This is an emerging area of research, but it suggests that the combination of morning light and morning caffeine may have synergistic effects on circadian alignment and morning alertness that go beyond what either provides alone. For evening chronotypes who are forced onto early schedules, morning light exposure is one of the most evidence-based interventions available. By consistently providing a strong light signal in the morning, even on weekends, evening chronotypes can partially advance their circadian rhythm, reducing the magnitude of their social jet lag and making early mornings somewhat less biologically brutal. It does not change their fundamental chronotype, but it can narrow the gap between their internal clock and their external schedule, which translates into better morning energy, improved sleep quality, and reduced health risks associated with chronic circadian misalignment. The bottom line on morning light is this: your circadian system evolved in a world where the first thing you saw every morning was the bright, blue-rich light of the rising sun. That light signal was the primary mechanism through which your internal clock stayed synchronized with the external world. In modern life, we have replaced that powerful natural signal with dim, spectrally impoverished artificial light, and we wonder why our sleep, our energy, and our health suffer. Getting bright light in your eyes within the first hour of waking is not a nice-to-have wellness bonus. It is a fundamental biological requirement that most of us are chronically failing to meet. The temperature clock, your body's hidden energy thermometer. There is another biological rhythm shaping your morning energy that most people never think about. One that operates entirely beneath your conscious awareness, but exerts an enormous influence on how alert, focused, and functional you feel in the hours before noon. It is your core body temperature rhythm. Your body temperature is not constant. It fluctuates by roughly 1 degree Celsius, or about 1.8 degrees Fahrenheit, over the course of every 24 hours, and this fluctuation follows a precise circadian pattern that is intimately linked to your sleep-wake cycle and your subjective experience of energy and alertness. The low point of your temperature rhythm, what scientists call the nadir, occurs in the early morning hours, typically between 2 and 4 in the morning. This is the time when your body is at its coolest, your metabolism is at its slowest, and your physiological systems are in their deepest state of conservation. If you have ever been awake at 3 in the morning, you know what this feels like. A bone-deep chill, a sense of profound lethargy, a feeling that your body and mind have slowed to a crawl. In the last couple of hours before your normal wake time, your body temperature begins to rise. This pre-waking temperature increase is not a response to your alarm clock or to getting out of bed. It is driven by your circadian clock, an anticipatory signal that begins preparing your body for the metabolic demands of wakefulness before you are even conscious. By the time you open your eyes, your temperature has already started climbing, and it continues to rise through the morning, reaching its daytime plateau by mid to late morning and its peak in the late afternoon or early evening. This temperature rise matters enormously for how you feel. Research has consistently shown that cognitive performance, subjective alertness, and physical capability all track closely with core body temperature. When your temperature is low, everything feels sluggish. Your reaction times are slower. Your working memory is diminished. Your mood tends to be lower. When your temperature is higher, you feel sharper, more alert, more capable. The temperature rhythm acts as a kind of physiological amplifier, boosting performance when the body is warm and dampening it when the body is cool. This explains, in part, why the very early morning feels so much harder than mid-morning, even after adequate sleep. At 6 in the morning, your core temperature is still rising from its overnight low. The biological amplifier is still ramping up. By 10 or 11 in the morning, your temperature has reached a level that supports optimal cognitive function, and tasks that felt difficult at 6 feel much more manageable. Now, here is where sleep quality intersects with the temperature rhythm in ways that directly affect morning energy. The timing of your temperature nadir is governed by your circadian clock, and as we have discussed, that clock is regulated by light exposure, sleep consistency, and genetic chronotype. When your sleep schedule is consistent and well aligned with your circadian rhythm, your temperature nadir occurs in the middle of your sleep, well before you wake up, and the pre-waking temperature rise is well underway by the time consciousness arrives. But when your sleep schedule is inconsistent, when you are experiencing social jet lag, or when your chronotype is misaligned with your wake time, the timing of that temperature nadir shifts. It may occur later, closer to your wake time, meaning that you are waking up at or near the lowest point of your temperature rhythm. This compounds the effects of sleep inertia, because research has shown that sleep inertia is significantly worse when you wake during or near the temperature nadir. Waking during the temperature nadir is not just about feeling cold. It is about waking up when every physiological system in your body is operating at its minimum capacity. Your metabolism is at its lowest. Your cognitive function is at its worst. Your cardiovascular system is at its most sluggish. You are, in a very real biological sense, waking up at the bottom of your daily performance curve, and the climb back to functionality takes longer and feels harder. This is one of the many hidden costs of irregular sleep schedules. A person who maintains a consistent wake time allows their circadian clock to position the temperature nadir well before the alarm, so that by the time they wake up, the pre-waking temperature rise has generated meaningful momentum toward alertness. A person who bounces between wake times disrupts this positioning, increasing the likelihood of waking during or near the nadir and experiencing a more severe and prolonged morning low. The temperature rhythm also helps explain why morning exercise, even gentle movement, can be so effective at accelerating the transition to alertness. Physical activity generates heat, raising core body temperature and essentially fast-forwarding the natural temperature climb. This is why a brief walk, some light stretching, or even a few minutes of movement in the early morning can feel disproportionately invigorating relative to the amount of effort involved. You are not just getting your heart rate up, you are manually pushing your temperature rhythm ahead of schedule, signaling to every system in your body that it is time to shift into daytime mode. And here is something particularly interesting for those who practice intermittent fasting or any form of time-restricted eating. Eating itself raises body temperature through a process called diet-induced thermogenesis. The act of digesting food generates heat, which contributes to the morning temperature rise. This is one of the mechanisms through which breakfast timing can influence morning alertness, not just through glucose delivery, but through its thermal effects. Eating a morning meal accelerates the temperature rise, while extending a fast keeps the temperature trajectory lower for longer. Depending on your goals and your chronotype, this interaction between eating timing and temperature rhythm is worth considering. The overarching point is that your core body temperature is a hidden metronome, beating in the background of every morning, and its rhythm is set by the same circadian clock that is regulated by your sleep. When sleep is good and the clock is well aligned, the temperature rhythm supports a smooth, efficient transition into morning alertness. When sleep is disrupted and the clock is misaligned, the temperature rhythm becomes another obstacle to overcome, another layer of biological resistance that makes the morning feel like an uphill battle. The architecture of restoration. What actually happens while you sleep? To fully appreciate why sleep determines your morning energy, you need to understand what is happening during those hours of unconsciousness. Because sleep is not a single, uniform state. It is a dynamic, architecturally complex process with distinct stages that serve different functions, and the proportion of time you spend in each stage directly determines how you feel when you wake up. A full night of sleep consists of roughly 4 to 6 sleep cycles, each lasting about 90 to 110 minutes. Within each cycle, your brain moves through several distinct stages, and the composition of those stages changes dramatically from the beginning of the night to the end. Let us start with what most people think of as the good stuff, the deep sleep. Scientists call it stage 3 sleep, or slow wave sleep, and it is the most physically restorative phase of your entire sleep period. During slow wave sleep, your brain produces large, rolling delta waves that sweep across the cortex in slow, synchronized pulses. This is when your body does its most intensive repair work. Tissues are rebuilt, muscles grow and strengthen. The immune system is fortified. Growth hormone is released in its largest pulse of the day. And critically, this is when adenosine, the sleepiness molecule we discussed earlier, is most efficiently cleared from the brain. Here is the architectural detail that matters. Slow wave sleep is concentrated in the first half of the night. The first sleep cycle typically contains 20 to 40 minutes of deep, slow wave sleep. The second cycle has a little less. By the third and fourth cycles, deep sleep duration has decreased substantially, and by the last cycle or two of the night, there may be very little deep sleep at all. This front-loading of deep sleep has profound implications. It means that if you go to bed at 11 and your alarm goes off at 5, you have cut your sleep short by 2 or 3 cycles, but you have probably still gotten most of your deep sleep. The early cycles, the ones rich in slow wave sleep, were completed before the truncation. This is why some people who get only 5 or 6 hours of sleep can still feel somewhat functional the next day, at least more functional than you might expect from such a short night. The deep restorative work got done. What they missed was in the later cycles. But what dominates those later cycles is equally important. REM sleep, rapid eye movement sleep, increases in duration as the night progresses. The first REM period, occurring about 60 to 90 minutes after you fall asleep, lasts only a few minutes. By the last cycle of the night, the REM period can last an hour or more. Over a full night, REM sleep makes up about 20 to 25% of total sleep time. REM sleep serves different but equally critical functions. It is the stage most closely associated with memory consolidation, the process by which your brain takes the experiences and information from the previous day and integrates them into long-term storage. It is also the stage most important for emotional processing. During REM, your brain revisits emotionally charged experiences from the day, stripping away some of the raw emotional intensity while preserving the informational content. This is why, after a full night of sleep, yesterday's problems often feel more manageable. The emotional edge has been softened by REM processing. When you cut your sleep short, you disproportionately lose REM sleep because it is concentrated at the end of the night. And the morning consequences of lost REM sleep are specific and identifiable. Without adequate REM sleep, your memory consolidation is impaired, making it harder to recall what you learned yesterday and harder to learn new things today. Your emotional processing is incomplete, meaning you carry unresolved emotional charge from the previous day into the new morning, contributing to that feeling of emotional rawness and reactivity. And your cognitive flexibility, the ability to see problems from multiple angles and shift between different mental frameworks, is reduced. The interaction between these two phases, deep sleep for physical restoration and adenosine clearance, REM sleep for memory consolidation and emotional processing, creates the complete picture of what a good night of sleep achieves. When both phases are adequately represented, you wake up with low adenosine, completed tissue repair, a fortified immune system, consolidated memories, processed emotions, and a prefrontal cortex that is ready to take on its supervisory duties. When either phase is shortchanged, specific aspects of your morning functioning are compromised. There is also a fascinating element of sleep's self-regulating architecture that is relevant here. When your body is sleep-deprived, it does not try to recover all lost sleep equally. Instead, it prioritizes. Studies have found that during recovery sleep after deprivation, the body recovers approximately 68% of lost stage 3 deep sleep, but only about 53% of lost REM sleep. Stages 1 and 2, the lighter sleep stages, are barely recovered at all, with only about 7% being regained. The body knows what matters most and directs its recovery resources accordingly. This priority system explains why a single, good night of recovery sleep after a period of deprivation can feel remarkably restorative. The body packs in extra deep sleep, accelerating adenosine clearance and physical restoration. But it also explains why full recovery from chronic sleep debt takes multiple nights. The REM sleep deficit, which is critical for cognitive and emotional restoration, takes longer to repay. The practical message is that when we talk about sleep quality, we are not talking about a single number. We are talking about an architectural balance, a ratio of light to deep to REM sleep that needs to be properly proportioned for the whole system to work. And the most common way that balance gets disrupted in modern life is not some exotic sleep disorder. It is simply going to bed too late and waking up too early, truncating the sleep period and disproportionately losing the REM-rich final cycles that are essential for morning cognitive and emotional function. When someone says, "I slept 8 hours, but I still feel terrible," the answer often lies in the architecture. Perhaps they drank alcohol, which suppresses REM sleep in the first half of the night. Perhaps they went to bed very late and woke very early, sleeping 8 hours but at the wrong circadian time, disrupting the normal distribution of sleep stages. Perhaps they were fragmented by noise, apnea, or temperature, getting 8 hours of clock time but not 8 hours of properly structured, architecturally sound sleep. The bottom line, your morning energy is not just a function of how many hours you spent in bed. It is a function of whether those hours contain the right balance of deep and REM sleep, delivered at the right circadian time, and allowed to proceed without disruption from beginning to end. The caffeine question. What that morning cup is really doing. No discussion of morning energy and sleep would be complete without addressing the elephant in the kitchen, the beverage that roughly 80% of the adult population reaches for within the first hour of waking. Coffee, or more precisely, caffeine, regardless of its delivery vehicle. We have already discussed the basic mechanism by which caffeine works. It blocks adenosine receptors, preventing the accumulation of sleep pressure from being felt. It does not create energy, it removes a break. And for most people, this feels like a net positive in the morning. You feel more alert, more focused, more ready to engage with the day. But there is a raging debate in the health and wellness world right now about the timing of that first cup, and it touches directly on everything we have been discussing. You have probably heard the advice, wait 90 minutes to 2 hours after waking before you drink your coffee. The argument, popularized by neuroscientists and wellness influencers alike, goes something like this. Your cortisol awakening response is peaking in the first hour after waking, so drinking caffeine during that peak is redundant at best and counterproductive at worst. Caffeine stimulates cortisol release, and adding exogenous cortisol stimulation on top of your natural car peak creates an unnecessarily high cortisol spike that leads to jitters, anxiety, and a more severe crash later. Better to wait for the natural cortisol peak to subside and then use caffeine to extend your alertness into the mid-morning. This argument sounds compelling, and it has been adopted by millions of people who now dutifully set timers on their phones and suffer through the first 90 minutes of their morning in a caffeine-free haze. But the scientific support for this practice is more complicated than its proponents suggest. Let us look at what the evidence actually says. First, the claim about cortisol. Yes, caffeine does stimulate cortisol release, but this effect is significantly blunted in habitual caffeine consumers. Research published in Psychopharmacology found that at moderate intake levels, around 300 milligrams per day, which is roughly the amount in 2 to 3 standard cups of coffee, tolerance to caffeine's cortisol-stimulating effects is incomplete but substantial. At higher intake levels, around 600 milligrams per day, the cortisol response was nearly abolished, with elevations occurring only immediately after the dose. For the majority of regular coffee drinkers, the concern about caffeine creating an excessive cortisol spike on top of the CAR may be largely theoretical. Second, the claim about adenosine. One of the key arguments for delaying caffeine is that you should wait for adenosine to clear before blocking the receptors so that the caffeine works more effectively. But as we discussed earlier, adenosine is cleared during sleep, not during the first hours of wakefulness. If you slept well, your adenosine levels should already be low when you wake up. There is no meaningful adenosine clearance happening in the first 90 minutes of your morning that caffeine could interfere with. And if you slept poorly, the adenosine is elevated, but it is not going to clear on its own by waiting 90 minutes. Only sleep clears adenosine. Waiting simply extends the period during which you feel the effects of that elevated adenosine without doing anything to reduce its levels. Third, the claim about afternoon crashes. Proponents of delayed caffeine argue that drinking coffee too early leads to a crash later in the day. But a research team that conducted an evidence-based scientific evaluation of caffeine supplementation literature concluded that there is a fundamental lack of evidence to support the idea that delaying caffeine intake in the early waking hours prevents an afternoon crash. The afternoon energy dip is more likely related to circadian factors, meal timing, hydration status, and total caffeine dose rather than the specific timing of the first cup. On the other hand, there are researchers and practitioners who continue to advocate for delayed caffeine on theoretical grounds. They argue that even if the current evidence does not robustly support the practice, the underlying logic about not wanting to add exogenous stimulation during the natural cortisol peak is sound, and that allowing the body's natural systems to operate without interference during the first phase of the morning promotes better long-term hormonal health. Some evidence suggests that chronic early caffeine consumption may, over time, lead to the body producing less cortisol on its own, increasing dependence on caffeine for morning alertness. There is also a chronotype-specific nuance worth considering. Evening chronotypes tend to have naturally lower morning cortisol levels compared to morning chronotypes, because their cortisol awakening response peaks later and is often smaller in magnitude. For these individuals, immediate morning caffeine may actually be beneficial, compensating for a weaker natural cortisol response and providing the activation that their circadian system is not yet delivering. For morning chronotypes with a robust car, the argument for delaying caffeine is somewhat stronger, because their natural activation system is already firing at full capacity. Where does all of this leave you? Here is what I think is the most honest assessment based on the current evidence. If you sleep well and have a consistent wake time, the timing of your first cup of coffee probably matters less than you think. Your adenosine is low, your car is functioning well, and caffeine consumed at any point in the morning is going to work effectively. If you sleep poorly, immediate caffeine is a band-aid that masks but does not resolve the underlying issue. It will make you feel better in the short term, but it is not addressing the elevated adenosine, the blunted car, or the metabolic impairment caused by the sleep loss. The most important caffeine-related decision for morning energy is not when you drink it, it is how much you drink and when you stop. Caffeine has a half-life of approximately 6 hours, meaning that a cup of coffee consumed at 2 in the afternoon still has half its caffeine circulating in your system at 8 at night. This late-day caffeine can delay sleep onset, reduce deep sleep, and impair the very process that determines how you feel the next morning. The irony is that for many people, the afternoon cup of coffee they drink to compensate for poor morning energy is the thing that is causing the poor morning energy in the first place. It is a caffeine trap, and the only way out is to address the root cause, which is always sleep. Putting it all together, the morning energy equation. So here we are, having traveled through the cortisol awakening response, sleep inertia, adenosine dynamics, glucose metabolism, prefrontal cortex function, appetite regulation, chronotypes, light exposure, body temperature rhythms, sleep architecture, and caffeine. It is a lot. And yet every single one of these mechanisms converges on the same fundamental truth. Your morning energy is not something that happens to you randomly. It is a direct, predictable consequence of what happened during your sleep. Let me paint 2 contrasting mornings to crystallize what we have covered. In the first morning, you went to bed at a consistent time, aligned with your chronotype. You slept for 7.5 hours. Your sleep was uninterrupted, allowing your brain to complete 5 full sleep cycles with adequate deep sleep in the first half and generous REM sleep in the second half. Adenosine was thoroughly cleared. Tissues were repaired. Emotional experiences from the previous day were processed and filed away. Roughly 30 minutes before your alarm, your circadian clock initiated the cortisol awakening response. Cortisol surged by 60%, mobilizing glucose, increasing heart rate, and preparing your neural systems for the day. Your core body temperature, which had been rising for the past hour, was already well above its overnight nadir. When your alarm went off, you, surfaced from a light sleep stage, so the transition to wakefulness was smooth, with minimal sleep inertia. You opened your eyes and felt clear. Not instantly energized, perhaps, but clear. The fog was minimal and dissipated within 10 to 15 minutes. You stepped outside briefly to get natural light, amplifying the cortisol response and calibrating your circadian clock for the day ahead. You ate a balanced breakfast, and because your insulin sensitivity was intact, the glucose was absorbed efficiently, providing stable fuel for your brain. Your prefrontal cortex came fully online within 20 minutes, ready to handle planning, decision-making, and emotional regulation. Your appetite was normal, your food choices were rational, and you felt satisfied after eating. By 8 in the morning, you were functioning at or near your cognitive peak for the morning hours. Energy was stable, focus was sharp, mood was balanced. The morning felt manageable, even enjoyable. Now consider the second morning. You went to bed 2 hours later than usual after scrolling your phone in bed. The blue light from the screen delayed your melatonin onset, pushing your sleep start time even later. You were in bed for 6 hours, but your sleep was fragmented because the circadian misalignment disrupted your sleep architecture. Deep sleep was reduced because your cortisol rhythm was shifted, and REM sleep was truncated because you had to wake early, despite the late start. Adenosine was incompletely cleared. Your cortisol awakening response was blunted and delayed because the circadian clock was confused by the inconsistent timing. Your core temperature was still near its nadir when the alarm went off, and you were pulled out of deep sleep, triggering severe sleep inertia. You opened your eyes and immediately felt terrible. The fog was thick and oppressive. Your prefrontal cortex was essentially offline, still waiting for blood flow to normalize and delta waves to clear. 15 minutes passed and you still felt confused and sluggish. 30 minutes, 45 minutes, the fog was not lifting. Meanwhile, your appetite hormones were out of balance. Ghrelin was elevated by 20%. Your endocannabinoid system was producing 30% more 2-AG than normal. You were ravenously hungry with a specific craving for high carbohydrate, high sugar food. And because your prefrontal cortex was impaired, the part of your brain that would normally resist these cravings was not functioning at capacity. You ate a sugary breakfast, and because your insulin sensitivity was reduced by the sleep loss, the glucose spike was higher and the crash was harder. By 10 in the morning, you were in an energy trough. Your blood sugar had crashed. Your adenosine was still elevated. Your emotional regulation was shot, and a minor frustration at work sent you into an irritable spiral. You reached for another coffee, which masked the fatigue temporarily, but did not address any of the underlying biological deficits. Same person, same life, completely different morning, and the only variable that changed was the sleep. This is what I mean when I say that sleep determines your energy before noon. It is not a contributing factor. It is not one item on a list of 10 things that matter. It is the foundation upon which every other aspect of your morning function is built. Cortisol, adenosine, glucose metabolism, cognitive function, emotional regulation, appetite, body temperature, all of it flows from and depends upon the quality, duration, timing, and architecture of the sleep that came before. The actionable foundation, what you can actually do. So what do you do with all of this? Let me close with some concrete, evidence-based principles that emerge from everything we have covered. Protect your sleep duration. For most adults, 7 to 9 hours is the range that allows for adequate deep sleep, sufficient REM sleep, complete adenosine clearance, and proper circadian alignment. This is not a luxury. It is the minimum biological requirement for your morning systems to function as designed. Treat sleep time the same way you treat a critical appointment. It does not get moved, shortened, or sacrificed for anything that is not genuinely urgent. Anchor your wake time. Of all the sleep hygiene practices available to you, consistent wake time may be the single most impactful. Waking at the same time every day, including weekends, trains your circadian clock to correctly time your cortisol awakening response, position your temperature nadir well before waking, and organize your sleep architecture so that you surface from light sleep rather than deep sleep at wake time. The temptation to sleep in on weekends is understandable, but the cost in social jet lag and Monday morning misery is real and measurable. Get morning light. Within the first 30 to 60 minutes of waking, spend time in bright, natural light. This is the single most powerful signal for synchronizing your circadian clock, amplifying your cortisol awakening response, and suppressing residual melatonin. On overcast days, the light outside is still dramatically brighter than indoor lighting. Even 10 to 15 minutes makes a meaningful difference. Respect sleep inertia. Give yourself a buffer of 15 to 30 minutes after waking before you need to perform at your best. Do not schedule critical decisions or important conversations in the first moments after your alarm. Use this window for routine activities, light movement, morning light exposure, activities that do not require peak cognitive function. Your prefrontal cortex needs time to come fully online, and trying to force peak performance before it does is like trying to sprint before your muscles are warm. Consider your chronotype. If you are an evening chronotype forced onto an early schedule, be realistic about what your biology can deliver in the first hours of the morning and build your day accordingly. Front-load easier tasks in the early morning and save high-demand cognitive work for the mid-morning or early afternoon when your biology naturally peaks. Use morning light exposure and consistent timing to gradually advance your rhythm as much as your genetics will allow. Be strategic about caffeine. If you choose to drink coffee in the morning, be mindful of total daily intake and, most importantly, of your cutoff time. Stopping caffeine by 2 in the afternoon, or even earlier depending on your individual caffeine metabolism, protects your sleep architecture and prevents the vicious cycle where afternoon caffeine impairs sleep, which impairs morning energy, which requires more caffeine. Whether you drink your coffee immediately upon waking or wait 90 minutes is far less consequential than ensuring it does not sabotage tonight's sleep. Pay attention to your breakfast. After a good night of sleep, your insulin sensitivity is at its daily peak in the morning, and your body is well equipped to handle a balanced meal. Prioritize protein, healthy fats, and complex carbohydrates that provide stable glucose delivery. After a poor night of sleep, be extra mindful of the hormonal forces pushing you toward high-sugar, high-calorie choices. Knowing that your ghrelin is elevated, your leptin signaling is blunted, your endocannabinoids are amplified, and your prefrontal cortex is compromised can help you consciously counterbalance these biological pressures, even if you cannot eliminate them entirely. Move in the morning. Even gentle movement, a walk, some stretching, a brief exercise routine accelerates your body temperature rise, promotes blood flow to the prefrontal cortex, and helps clear residual sleep inertia. You do not need an intense workout. You just need enough physical activation to nudge your temperature rhythm and blood flow in the right direction. And finally, stop blaming yourself for bad mornings. If you understand the biology we have covered today, you understand that a morning where you feel foggy, irritable, hungry, unfocused, and unable to function is not a character flaw. It is a predictable biological outcome of disrupted sleep. The appropriate response is not self-criticism. It is curiosity. What happened with my sleep? What can I change tonight to give my body a better chance tomorrow? That question, asked with genuine curiosity rather than judgment, is the beginning of real change. Your mornings are not random. They are not luck. They are the expression of a profoundly complex, exquisitely calibrated biological system that depends on one thing more than any other: the sleep you give it. Get that right, and everything else about your morning will follow. If this information changed how you think about your mornings, do me a favor and hit that like button. And if you want to keep going deeper on topics like this, sleep science, circadian biology, intermittent fasting, and everything that contributes to living an optimized life, subscribe to the Optimal Life Project and turn on notifications so you do not miss what is coming next. I have got a lot more to share with you, and it only gets more interesting from here. Thank you for spending this time with me. Now go get some sleep.